Okay, sounds like we're live, so I'm going to go ahead and get started. So I'd like to welcome everyone to today's NANOG outreach meeting. I am Eddie Winstead. I work for Internet Systems Consortium. You probably most likely know us as the makers and maintainers of Bind, DNS software. It's open source and free. And we also make ISC DHCP and Kia, which are DHCP protocol implementations. We also run one of the 13 root name servers, froot, and I'll be talking about root name servers in this talk today. So this is DNS fundamentals. So I want this to be as interactive as possible. I know that we're all pretty much burned out on Zoom these days, but if you would please enter in questions in the chat. Unfortunately, I can't see them in real time, but one of the NANOG folks will be relaying those to me in the chat that I have here. So right off the bat, if you have any questions, go ahead and put them in the chat. I'm going to try to address them as we go along instead of doing the traditional Q&A at the end. All right. So the DNS. Well, let's talk about it briefly before I get going with the slides. So a lot of the things that people say about the DNS are, it is the phone book of the internet. So in today's internet, of course, we're running over internet protocol, right? And we have been since way back in 1983. The internet speaks, this protocol is based on IP addresses, internet protocol addresses, right? So in IPv4, they're a little shorter. In IPv6, they're a lot longer and we have a lot more space, right? But we as humans have a hard time remembering numbers as well, most of us, remembering numbers as well as we do text, right? So this, you see my name here, and then you see, information about the company that I work for. This www.isc.org is much easier for us as humans to remember than the IPv4 address, and certainly the IPv6 address of that website, right? So, I say to folks a lot of times, like my mom always asks me, "What is it you do again?" Right? And it's essentially names to numbers and numbers to names, right? So I have a question for you, and feel free to put it in the chat, and hopefully it can be relayed to me. But how many of you thought about, when you joined this webinar, how that transaction was happening, right? You probably went to nanog.org and you clicked on something, and in the background there's all these translations going on, right? You are, as a human, looking for www.nanog.org, and that is being translated to an IP address or several of them, and you're getting to the site that you intended to get to, right? So again, how many of you thought about that when you started clicking on things, right? How many of you thought about this morning, whenever you woke up and you checked your email, whatever you do first thing in the morning, right? We all grab our phones now, right? How many of you thought about the DNS transactions that were happening on your behalf, right? If you haven't thought about these things yet, I really encourage you to do so. To me, the DNS is a fascinating part of the core functionality of the internet, right? But it's one that very often in a lot of organizations is taken for granted, right? No one really thinks about DNS until, of course, the DNS is not working. It turns out, those of us that are, internet professionals, or I know we have a lot of students on today, you're going into this field, it turns out that the internet actually works without the DNS, right? The numbers usually are working just fine, right? But if there's a problem with the DNS, then for the humans, this gets to be a problem. Okay, on to the slides. So, yeah, so this internet thing. So this is an actual network map from way back in the day. So we had this internet that was started via DARPA called the ARPA network. And this is the actual map of the first 4 nodes on this, right? So this is way back in 1969 We had, SRI at Stanford, UCLA, UCSB, and Utah. All right, everything's great. Well, somewhere along the way, we started thinking, we're going to have to start naming these things on this network. So way back in 1971, RFC 226 started talking about the standardization of host names. Okay. So for those of you that don't know, an RFC is, as if you can see in the upper right corner, a request for comments. And this is done via the work at the IETF, the Internet Engineering Task Force. If it's the first time that you've heard of these things, RFC and IETF, I highly recommend that you search those, either right now or after the talk, because if you're going into this field of internet operations or architecture, whatever it is you're doing, or security, these are the things that these are extremely handy tools to actually, like, you can read how all this was developed. Now, fast forward to 1983. Again, this is when we transitioned over to the TCP/IP model. The network, obviously, at this point is much larger, right? So here, obviously, lots more educational organizations, and then we're also starting to see some commercial organizations here. These here, this research institute over at Stanford, this was essentially the place where we started having a consolidated place of management of the names. Okay. So I suspect no one is old enough on this call, maybe other than myself, to remember actually managing things with a host.txt file. Okay, as the name implies, it was a text file. This contained information about hosts on this internet that we had at the time. It was maintained by the folks at SRI. You could send an email, to the folks at SRI, and they would do updates for you in the DNS. Well, sorry, this is pre-DNS, so they would do updates in the host.txt for you. So these were rolled out twice a week per FTP. They were rolled out twice a week, also available via FTP. So can you imagine in today's internet, any device that you want to add to the network? Well, for the naming purposes, it's going to take about 3 to 4 days for it to show up. That in today's internet world would be entirely unacceptable. Back then, just fine. Devices were expensive and just weren't being added very often. All right. Now here's an example, an actual example of what was in that host.txt file. So you see we have some IP addresses here. Again, these are IPv4, and then you have information about this particular host. Now, one thing that may stand out to most of us today is this is not only the number and the name, there's also information about these hosts. Back in the days of host.txt, the internet was a very small neighborhood. We all kind of knew each other. And so you could do things like, hey, on this host, I run things like Telnet, FTP, et cetera, et cetera. They're available there. In today's security-minded internet, you would never do this. The neighborhood is not small, and all the actors are not known, and a lot of the actors are not there to do quote unquote nice things. Okay. So far, everyone, I have not got any questions in the chat, and I really hope that we change that. Send me some questions. All right. Okay. Now, some of the things that you might have already thought about is, oh my goodness, again, like I was saying, in today's internet, having stuff attached to the network without a DNS entry almost immediately is sort of frowned upon, right? So that was one of the problems. The other thing is, we had a single entity that was maintaining these entries. Often people there would want to take a vacation or whatnot. So this becomes a problem. And then as the network grew, there started to be namespace collisions, right? Some people wanted the same names, right? So this is a problem. So 83 was around this time that, again, these were big changes in internet history. TCP/IP came about, and also when we started focusing on something had to be done to change this. So the first DNS-related RFCs happened around in the early 80s. So you had 1981, RFC 799, Internet Name Domains. And then the really two core ones were 882 and 883. And again, this was in 1983. And let me check the chat one more time. No questions, that's fine. So one thing I really want to stress here is the core of what the DNS is still in 882 and 883, right? So this is a 30, wow, it's 30 some years old, right? This protocol that is still being used for the core of the internet. A lot of us thought this thing just wouldn't scale to, I mean, we couldn't really conceive of it back in those days, right? But it has scaled very well, and I'll show you, we've actually made a lot of changes to the DNS and how it operates. Okay, I do have a question now. Who approves the RFC? Well, that's a complicated question. So any of you that are aware of the IETF know that there's quite a process, right? So in the Internet Engineering Task Force, you have what's called working groups. One of the more popular ones is DNS Op, which talks about DNS operations. And so there's a very long process where you put out a document, RFC, and you request comments on it. So there's discussions in the working groups. The IETF, in the before COVID, met 3 times a year. So there's a lot of in-person back and forth about differing concepts that folks want to propose as a standard. And now with COVID, the IETF is still meeting. It's all virtual. Those of you that, again, are seeking out employment as in internet industries, take a look at the IETF. This would be a really good time to try to attend one virtually, right? Because they're all virtual at this point. Anyway, there's also mailing lists and blah blah blah. There are ways that this in the technical community that participates in the IETF for folks to be heard, and some of these, frankly, turn into some pretty long, drawn-out battles, right? There are very strong-willed folks involved in the IETF, and so there's a lot of back and forth about what we're going to do, what is the right thing to do. Anyway, all that process takes place in the IETF. So there's really no one party that approves the RFC. It's a long process of trying to get consensus within the community that this is the best path forward for a particular design. And yeah, okay, I hope that answered that. All right, back to the slides. Okay. So fast forward to what year is it? 2021, and these are all the current DNS RFCs. So as I mentioned, the core of the protocol is really old, but as you can see, there have been a lot of updates to the functionality of the DNS. There's an old saying that almost every problem in the internet, at least one person will come up with, well, let's fix that with the DNS. So it's sort of a joke, but there has been a lot of cases where we have tried to fix a lot of the internet related problems with the DNS. Okay. Let's see. This Bind 9 Administrator Reference Manual, again, I mentioned earlier, Bind is the, it's sort of the de facto standard for DNS implementation. It is open source. Back in the olden days, it was kind of the only party in town for open source DNS software. These days, we have a lot of friends that also produce DNS software. If you're interested in getting into the DNS in terms of learning, one of the things I highly recommend is downloading DNS, open source DNS software and playing around with it, right? Become your own resolver. I'll talk about resolvers a bit later, but it's a good way to learn what's going on underneath. Again, this whole concept of starting to think about, when I type in something, what is happening on the back end to give my device the appropriate IP address that I need to connect to, okay? So anyway, in Bind 9, we always keep this up to date. There's a big bibliography of current DNS RFCs, okay? Okay. All right, so what did we want to do with the DNS? Again, backtracking back to like 1983, the idea was, of course, the namespace was exploding. Everyone was starting to see this thing is going to get bigger than we sort of imagined, or that the early folks imagined. The other thing that's really critically important is this whole idea of delegation of responsibility, right? So if I run the zone isc.org, I should be able to make changes, or anyone that works for ISC should be able to make changes to that zone that then other folks in the world can see, right? So if I want my web server, the one that we always think about, if I want my web server to live on one certain IP address, then I can put that in my DNS for isc.org, and then the rest of the world can look that up, okay? So I'm going to go ahead and mention these two terms right now. These are two very important terms in DNS protocol. So authoritative and recursive, right? So authoritative means, how do we get the data into the DNS what's the right word? I'm looking at database, but it's not really the right word. But anyway, how do I get this? How do I get some data into the DNS, right? I put that in on an authoritative server, right? And I'm going to take you through how this works on the back end in a bit. I just want to get these concepts in your brain. Now, on the other side is, how can someone look that up, right? Clients typically ask what's called a resolver, right? So a resolver works on behalf of the clients to go out and do the DNS work to look up the authoritative source, in this example, isc.org, and send that back to the recursive resolver, which then sends it back to the client. Okay, so authoritative and recursive, these are two very important parts of the DNS protocol. All right. It turns out a design goal back then was also that we wanted to minimize network traffic. Now, you youngsters of today will sort of giggle, right? Because you're watching a video feed of me live, talking about DNS and talking about minimizing network traffic. It's kind of funny now, right? In those days, host.txt, just a text file, but in those days, the networks were slower and actually quite costly to send traffic over, right? So we needed something to provide this naming, but not take over the networks, right? We didn't want a lot of network traffic. And then, we wanted a single mechanism for looking up names and looking up addresses, right? Names to numbers, numbers to names. And we wanted something extensible. And really, the designers of the DNS, Paul Monkapetris, John Pastel, they really did a great job of designing this protocol to be extensible. Because again, the very basics of it are still intact, right? We've added a lot to it, but it has scaled extremely well. Okay, so more design goals. Yeah. The other thing is it was clear that the internet, of course, it was very US centric when all this was designed, but it was very clear that this was going to be a global internet at some point, right? So this needed to work throughout the world, and it needed to be able to scale. And again, the scalability has just been really amazing, right? We have folks that I've worked with that do, they handle 1 billion DNS queries a day. That's amazing, right? And again, it's on the very basics of this design that I'm talking about. Now, before I get into this, I want to point your mind back to that host.txt file, right? This whole idea that, I would share things that in today's internet we would think is insane, right? I'd never want to tell you what services I'm running on some device, right? For security reasons. So I want you to think about that security was not on the list of things for the DNS design, right? So what does that mean for you? Again, start thinking about when you type in a name, what is the security behind that? How do you know you're getting the right response? You're getting it from the appropriate parties, right? So we'll talk about some of that as we go along. So basic DNS theory here. So this slide has two purposes, all right? So I'm going to talk about the DNS namespace, but we've also got these. So I want you to look at the little yellow dots, right? Those are what we would call nodes in the namespace. And then I have some servers listed here. Those are just to sort of put in your mind that, of course, these servers are providing the implementation of this namespace, all right? So a lot of people talk about the DNS as an upside down tree, and it is. There's a top level, and then there's many layers underneath. So the main one that you may have already heard about is root or dot. Okay, so dot is sort of beginning of the DNS. Each of these nodes can be up to 63 bytes long, blah, blah, blah. But the first level down is what we refer to as top level domains. So you have root, and then below that, you have, in this example, you have Alpha, Bravo, Charlie, et cetera, et cetera. Those would be your top level domains. Now, in practice, so this is talking about theory. In practice, those top level domains are things like .com or .org, .net, .us. There's lots of them now. And then the ones below that can either be third level domains, or they might be subdomains of the top level domain. We'll talk about all that. Now, it's important that these must be unique for sibling node, right? So I can have 2 kilos at the third level, but I couldn't have the two kilos at the top level, right? It has to be unique at each level. The reason I can have them at the second level is because then I have kilo.bravo. And kilo.charlie, right? What were the original top level domains? That's a great question. So this is a question that came in from the chat. What are the original top level domains? Someone may need to use Google to see if I can get all of them. All right, so there was .mil, which is obviously US military, .gov, which was US Gov. There was .com, .net, .org. That's 5. There's others. So if anyone wants to add to the chat, that'd be great. I used to have a slide on this, which is funny. Yeah, .us. So I don't know if the other question becomes, what were the originals, right? At what time frame, right? It seems to me that .us was added a little bit later, but I might be wrong on that one. The locality-based domains, I think, came a little bit after the original top-level domains. So .us is now a top level domain, as is like .uk, .in for India. You know, there are, I want to say 200 and some official locality-based domains, and they're based on, yeah, .edu, thank you, that was one of the originals. So the locality-based domains are usually named for the country code that is associated with that particular country, right? Good questions, keep them coming. All right. So a domain name, you often hear us speak of domains and domain names. So in this case, you know, these are unique for a quote unquote given node. Again, in this part, focus on the dots, right? So here I'm highlighting alpha. So you can say things like, this is the alpha domain. You can say golf lives in alpha. So you could say golf is an alpha domain, right? Just like you would say something like ESPN is a com domain, right? So ESPN.com dot, right? So if you get into the DNS as part of your profession, I'll just go ahead and warn you, adding that trailing dot is critically important. Because if you don't add it, then it's ambiguous, right? Golf.alpha could actually exist in Bravo, right? So you could have golf.alpha.bravo dot. But if you add that dot on the end, golf.alpha dot, then you know exactly what that domain is, okay? So this is just sort of, you know, I often speak ahead of my slides, so here I am doing that again. Fully qualified domain names have the dot at the end. We often refer to it as a trailing dot. So in this case, for this example, we would have lima.golf.alpha. As the fully qualified domain name for this lima.golf.alpha domain, okay? Now, every node contains data. And again, I'm just showing you the computer there because, you know, the computers are, oh, sorry, I got a question coming in. Except for the zillions of modern tools that think a trailing dot is an invalid domain. Now, that is a valid point. I can't, you know, you will find, how do I say this nicely? Okay, the speed at which new devices are coming on the internet outrun the ability for the humans that are creating those devices to be fully aware of all of the RFCs that they should be aware of. Okay, so you'll see devices and tools and apps doing really insane things, right? You know, in the end, a lot of these cases, you know, I have a mind for, you know, the business model as well, right? My official job is sales engineer, so I sort of straddle the technical and the business sides. But in a lot of cases, you know, as long as there's a product that people pay for, then you know, it doesn't matter to the creator that maybe they're not following the RFCs exactly. And someone pointed out .arpa, which is like, you know, I should slap myself in the head for forgetting that one as one of the originals. So the .arpa is the inverse or the reverse, right? So the numbers back to the names. Okay. All right. Good stuff. Please keep me on my toes. All right. So back to this. Every piece of DNS data is going to have these 5 parts. Okay. Always going to have owner, always going to have TTL, always going to have class, always going to have type, always going to have data, okay? Owner, very simply, if we go back to the example that I had before, like www.isc.org, right? This is what I'm trying to put into the DNS on my authoritative servers, right? I'm trying to add this so that the rest of the world can look up this data. Now, TTL is something that you probably can sort of guess if you've never heard of it. TTL is time to live, okay? as the authoritative source for ISC.org data or your domain's data or whatever, I, as the administrator, can put in these, let's call them recommendations for how long you can keep this data. Okay. Remember, one of the original design goals was to limit network traffic. One of the ways we do that is on these authoritative servers. I add data in there that says to the recursive servers, the ones that are doing lookups on behalf of the client, I can add data that says, hey, this address, pretty static, right? You can keep it and serve it to your clients for 2 weeks, right? In the old days, believe it or not, there was a lot of DNS data that said you could keep it for 2 weeks. These days, 24 hours is sort of a max, right? Because things change in today's modern internet. But anyway, you can have really high TTLs. Not a problem as long as that data isn't going to change very often. And again, that design is part of how we were limiting network traffic. Now, class, for the purposes of our talk today, we're going to be talking about the internet class. If you've actually worked on a name server before, this would be represented as IN, or internet class. 99.99% of the things we do in the DNS are internet class. There are other classes. Rarely are they used. They were defined to be used for other things, but over time, IN is what we all use. Very, very small cases, we can use these things to like query for information in other classes. But anyway, for today's talk, we'll be talking about the IN class. And then type. So in the example of a www entry, type would usually be A, right, for address. I'm adding an IPv4 address into my authoritative data. Or it could be quad A, right, because IPv6, right? I want to add an IPv6 address. And then the data portion in the node is exactly that. It's the data, right? So if I'm adding www.isc.org, then I'm going to add something in the data that's my web server for that entry, right? So something like 149.20. Blah blah blah, something, right? An IPv4 address. Okay. So very often when we start thinking about the DNS, a couple of things happen, right? Even in my brain, right, I always sort of focus on things that exist, right? So in the DNS, though, we have to have a way, and again, we're still talking about DNS theory, we have to have a way that says that something doesn't exist, right? Because we know we're going to not be able to type well, right? So somebody's going to try to look up www.isc.org, right? Oh, and someone has just pointed out Hesiod class. That's very nice. So at least they don't need chaos records. So sorry, someone's sending in chats that are pretty funny to me. So that's good. Yeah, this is, yeah, I won't in case you don't want me to, I won't acknowledge who it is. So, but anyway, yeah. So, but again, back to this, I have to have a way for the DNS to come back to the client and say, you ask for www, or you ask for www, and that does not exist. So I have to have a way for the client to get back what we refer to in the DNS as an index domain. This does not exist, okay? There's another one of these that's very similar, and that is a no data response. So say someone typed in the right name, they're looking up www, but they're looking for something, and this is later on in DNS history, they're looking for example, like an SRV record, which is a service record. In this example that I'm speaking of, there is no SRV record, right? But the node exists, right? Because you asked for www and you asked for an A record. You asked for an SRV record, but the A record exists, right? So what you get back is what's called a no data response. Okay. Now, for those of you again that want to, and based on at least that last chat, some of you already are doing some sort of DNS administration. There is a tool called Dig, right? So I highly recommend that any of you, again, my prior recommendation was to download some DNS software, start to play with it. That's great. If you don't want to go that far, you can start using tools like Dig. Again, the way to get Dig is you have to download at least part of the software. There's information on this online. Go to ISC's website. You can find out how you can get Dig. Some servers already have it, right? So you may be at an organization that already has Dig installed. But anyway, this is a way that you can start looking at the DNS responses coming back to you, right? You can dig for certain things. So instead of like lookups happening because someone is trying to reach the service, you're actually doing manual lookups because you want to make sure that they're coming back right. It's a debug mechanism, essentially, right? Let's see. Got another chat here. That's a good one. Adam Thompson. he's the one telling me, pointing out all the different records. Yeah. So it's good. All right. Yeah. He also points out that, and I'm going to get into some of this later in the talk, but this is all like really simple DNS theory as it was designed. And then, people happen to it, right? There's insane requests of things that people want to put in the DNS. There are insane requests of the things that have actually been put in the DNS. And so this so far all looks pretty simple and straightforward, but in practice in 2021 DNS land, it's pretty insane. So again, when you start talking about billions of queries a day, there's a lot going on in the DNS. An interesting point on that, as I said earlier, ISC runs froot, and amazingly, I think the number is something like 97% of the traffic that the root servers receive is basically junk. It's people doing bad queries. It's people not caching properly. It's just kind of insane. All right. Okay, back to this. All right. A domain, very simply, is a subtree of the namespace. So here, I'm pointing out the alpha domain. I've talked about some of this a little earlier as well. Most of us, sort of our brains go to like .com, you can say it com dot. And I've also received a chat that says people happen to it is going to be used. So that's good. Yes, that does happen. Com dot is like the official, is probably the more proper way to say it, right? We're fully qualifying it. Now, these days, you all probably know that there was the original set of domains, top level domains. There was the country code based domains and CCTLDs. And then over time, and I won't get into, there's a lot to this, right? So I don't want to get into the political aspects of this, but or layer 9 aspects, but there are a lot of top level domains now, right? So whether you think that's a good idea or not, we won't get into that. In terms of 2021 DNS, there are a lot of top level domains, right? Things like .black, .blue, .red, you name it, it's probably already out there these days as a top level domain. And then a subdomain is very simply a domain that lies within another domain, right? So we have the alpha domain, and then in this case, we have a golf subdomain. Okay, but these are terms that you'll hear all the time, right? I have a domain, I have a subdomain. Very common. When people speak of the DNS, this is what they're talking about in this regard. Now, Remember earlier I mentioned one of the really core and important design goals with DNS was delegation. Okay, so if I go back, so in my little dots here, I'm delegating. So this alpha node is being delegated out, right, from dot. And then the same way, this golf is being delegated out from alpha. Now, if you take your mind's eye to the devices that are sitting there, so if I go to alpha here, that server, so for simplicity, we'll say there's one server running DNS authoritatively for alpha. We know that's not the case in the real world, but just for example, alpha has a server, and in the DNS data, authoritative data for alpha, there will be what is a delegation record. So it's called an NS record. It will exist in alpha and it for golf, and it points to golf's name server for simplicity, the one server there that's sitting there serving authoritative data for golf, right? So again, this delegation is critical to the design, right? Because again, we don't want to have one entity maintaining all the DNS. So we have root servers, right, that are spread out all over the world, and they provide data from root, and they have delegations for all the top level domains. And then all of those top level domains are run by other parties, and they have delegations out to whoever is quote unquote registering that domain. So for back to the isc.org example, if I'm ISC, I talk with the org folks, that's my parent domain. I get them to put in an NS record that establishes the delegation to my authoritative server for isc.org. Then once that's in there and I've set up the domain on my server, then as people start to query for my name, eventually they're going to find my server, and then they're going to be able to get my authoritative information from my server. Okay. All right. So again, delegation is critically important. This is referred to as the chain of authority in DNS terms. All right. And again, I've talked before my slide, and so yeah. I was pointing out all that stuff on the prior slide, but this is exactly what I was talking about. I'm not going to redo it. But again, this delegation occurs between the parent domain, alpha, down to golf in this case. Golf can actually, there could be two scenarios here that would work, right? Golf could add, if we just talk about the dots in terms of nodes, golf could add those nodes in its zone file and have them in that zone file. Or golf can also do delegation records down to Kilo and Lima, right? So again, the delegation is critical in the design. All right. So name resolution. All right. So back to this whole all DNS has these 5 things, right? So here the owner in this example is the domain name. So we're looking up example.com. We're looking up internet class, and we're looking up the type of data. Okay, so very importantly, these are the things we know as the client, right? Okay, I want to go to obviously this website. And so DNS wise, I need to look up this information so that I know what IP address, or my machine knows what IP address that we can go to or need to go to. So when we do this, this is what we learn, right? I get back the IP address or a resolver gets it back on my behalf and then gives it to me, the client. And then also what comes with that data is the time to live. So again, this is about assisting with having less network traffic for the DNS. Typical ones you see these days are really like an hour, right? This, you can cache this for up to an hour, for example. All right. So now let's take a look. Let me just check the chat. We're good on that. All right, so let's take a look at the actual name resolution process. So again, this is what I want you to, if you haven't already, to start thinking about. When you're sitting at your laptop or your phone, what types of DNS queries are you generating? It turns out, which is really sort of amazing, if you do any, if any of you do sort of any like packet tracing or just sort of watching your network, it turns out these days you might visit one website and most likely there's about 50 to 100 DNS lookups that happen, right? Because in today's internet, you have, it's all about, well, a lot of it is about ads, right? So there's so many lookups happening on the back end for ads that are being served to you, et cetera, et cetera. Or you're going to a website that, they have partner websites that provide part of the data. Anyway, it's pretty insane the amount of DNS lookups that are happening just for you to visit one web page. But so here you are on your little laptop, and you're looking up, how do I get to www.example.com? All right. So you're sitting here in this case, you're on this laptop. This laptop is probably connected wirelessly, right? Wherever your access point is, there's usually either they give you, however you're getting connected via DHCP or whatever, you're directed to ask your DNS queries to usually a local caching DNS server. Again, back to this terms I was using earlier, this would be called a resolver, right? So you have a resolver acting on behalf of the client. Now, in these days, this isn't always the case, right? It might not be exactly local. You can have sometimes people point you, in the old days, right? This local caching DNS server was almost always either your enterprise name server sitting there on your campus wherever you were working, or your university, or if you were connecting from home, this was almost always your ISP's DNS server, right? These days, you can probably guess that a lot of people point for various reasons to other name servers, right? They point to the most common ones: 8.8.8.8, 9.9.9.9, 1.1.1.1, right? There's various reasons that you would use these. The most common being the Google's name servers: 8.8.8, 8.8.4.4, okay? Anyway, so back to DNS theory. I'm a client. Whatever mechanism I use to connect to the network often gives me the DNS server to use. So I'm asking that DNS server, what is the address of www.example.com? Now, again, just stepping back one moment, so start thinking about the security here and start thinking about the data, right? There's a lot of money that is made on the internet based on data, right? So there are reasons that you would choose to use certain name servers or not, right? So start thinking about this. I talk to my kids a lot about, Adam would probably like this one, but I show my kids query logs, right? So I see what you're looking up. So it's important for you to know, like security wise, nothing really is private here, especially when I am in clear text asking a certain question, right? So again, DNS wasn't designed for security. There's some ways that you can help that. There's also encrypted DNS. We'll talk about that a little bit later. But anyway, so back to our example. I've got a name server that I'm using for whatever reason, whether I chose it or my provider chose it for me. I asked the question, what is the address of www.example.com? So just assume that this local caching resolver, yeah, very good, Adam. This local caching resolver, just assume that it just booted up, right? So do I have the address of www.example.com in my cache? The answer, of course, if I just booted up, is no. When a resolver first boots up, all that it has in its configuration is what's called root hints. And this is the addresses, the IPv4 and IPv6 addresses of the root servers, right? Once that, and that's really just a priming query, because once that goes out, then when queries start coming back, this caching server will learn the current addresses of all the root name servers. They don't change often at all, but the first one that goes out is just, we refer to it as a priming query. All right. So anyway, this box says, nope, I don't, do I have this in my cache? The answer is no at this point. So it turns out then that all I know about, as I said, are the addresses of the root servers. So guess what? As the DNS is designed, I'm going to ask, this resolver is going to ask the address of www.example.com, and it's going to ask it to the root servers, right? You may already be seeing some other privacy concerns in the original design. They do exist there, right? There's a thing now called QName minimization. And so it's a way for, based on configuration, you can have the caching servers say, I don't know about example.com. So instead of asking the root about, example.com, I'm just going to ask the root about com and get the information I need. And then I'm going to proceed down the chain. All right. Again, one of those things that those changes that we've made to make the DNS better, more private, more secure, etc. All right. So, of course, root isn't going to know about example.com. All root is going to know about is com in this case, in terms of what's applicable to the question that was asked. So what the root does, the root servers do, the one that you talk to, sends back a list of all the com.name servers, right? So essentially, I don't know, but here's some information that will help you. In DNS terms, this is called a referral, okay? So we work our way down. Now I know where com is, so I ask com, again, as originally designed, the full question. What is the address of www.example.com? Again, I'm going to get a referral because com doesn't know that specific answer, but it does know the name servers for example.com. The way it knows that, again, as we talked about earlier, is because there are NS records for, delegation NS records in example.com that point to the actual authoritative name servers for example.com. Again, this delegation part that is critical. So that's what the com servers send back to this resolver. I also want to point out, this local caching server is recursive, and all the ones that I'm listing here on the right-hand side, those are all authoritative, because remember, on the authoritative side, that's where we put in data to the DNS. On the resolver side, that's clients trying to seek out what that data is. All right. So now in this simplified case that I know the name server for example.com, now I can ask that question again. And I'm sorry, this slide should say www.example.com, but I think it got clipped off in one of the updates to the slide. So my apologies there. But again, I'm going to ask that full question, but this time to the name servers for example.com. Now I finally, and again, this should say www.example.com. I get that back, and now I've finally gotten an answer to my question. All right, good stuff. The resolver has it, and now it can provide that response back to the client that originally asked the question. Okay. Now, I think my next slide is probably on caching. Yeah, very good. I didn't talk over it this time. So the beauty here is, I had to do a lot of queries at first, right? Because I had just booted up this resolver. But now my client is asking for ftp.example.com, right? So I already know the name server for example.com, right? So now I don't have to do that, asking all the way down from the root. I can just go ahead and say, okay, I do a check. I don't have FTP, but I do know example.com, right? So now I can just ask that question directly to the authoritative name server for example.com. I don't have to do the walk down from the root. I get that back to my resolver, and then that can be fed back to the client, okay? So again, the resolver will keep the name servers for example.com based on whatever me as the administrator for example.com set as the TTL. Okay. Yeah. So recursion versus iteration, right? So this is recursion and iteration. You'll see a lot in DNS terminology. And in this case, like for this client, the client had one question, right? Uh, in the first case, the resolver had to ask 3 questions. Each of them sent data that they were authoritative for. So in DNS terminology, what we would say is this client sent one recursive query. So the one query came in was recursive. These other ones are called iterative queries. That's a hard one for me. But yeah, in DNS terminology, this is what we talk about. You'll hear a lot about recursive queries. Again, if you get into the DNS ecosystem as your one of the, if you become a DNS administrator, most of them live on one side or the other, right? So you'll have very large authoritative operations, right? So you say maybe you run the name servers for com, or on a smaller scale you run the name servers for a company, and your responsibility is inserting authoritative data and deleting and modifying that authoritative data on the right hand side of the screen, right? You're focused mainly on authoritative. Then the other side of the equation is on the recursive side. If you are, say, a DNS administrator for like an ISP, then the majority of your DNS life is going to be lived on the recursive side, right? You run this server on the left side, and usually you run many of them, okay? If you're answering 1 billion queries a day, that's pretty extreme. But if you're answering, even 100,000 queries per day, 1 million queries per day, you're going to have several machines to take care of that. Okay. Yeah, so this was all DNS in theory, right? So that's how the DNS was designed, and that's great. This is DNS in practice today. So, there's really just, you can't draw it on a slide as what is actually happening in the DNS, right? So if I go back one slide, again, this is very simplified because I've already told you there are 13 root servers, right? It turns out there are thousands of root servers actually in operation, right? So we use a lot of tricks these days, like Anycast, that allows us to have multiple servers answering on the same IP address, right? So there are 12 root server operators. We all have our different ways in which we provision our machines. This is good, all right? This is what keeps the root healthy and what's the word I'm looking for? Anyway, provides consistent service, right? If one root server operator has a problem, there's 11 other ones that are still rolling, right? It's a way to keep problematic traffic locally, right? So if I had servers that, if it's still in the old days where there were actually only 13 actual physical servers, then one of those could get into a lot of trouble. But if I spread all that out, then suddenly I have 50 root servers in across the world. Then if there's a problem in terms of like traffic in one area, it usually doesn't affect the whole, right? So same thing for .com. The .com, there's not one server that serves .com. There's at least 13 listed and many, many more than that, right? I say 13 listed in the DNS, right? But again, with tricks, modern tricks like Anycast, we're able to provide many more servers to provide this data. Same thing even on the domain level, like example.com. If you're a huge provider, You can think of all the ones that are huge, right? The Amazons, the Googles, all of those authoritatively are going to have a lot of name servers, right? And then on the other side, on the recursive side, again, I talked about this a little bit before. If if you're on the ISP side and you're serving millions of queries a day, you're not going to do that with one box, right? So what does that mean for the client? The client doesn't care, right? The client just wants to get their question answered. But there's got to be some trickery on the recursive side that the client gets to one of your name servers, resolvers, and then that resolver can go out and do all the work and send the query, the answer back to the client, right? So you can use Anycast on that side as well, right? So you could have as many servers as you need to handle the load, um, uh, and have them answering on the same address. You can also do things like load balancers, right? This is, the DNS is just a massive service these days, and as we talked about, critical to the experience, the user experience, shall we say, right? So you want these queries going out fast. You want them coming back fast. Now, this brings up some other points, right? If we were in a class, I'd be asking you all questions, right? But the main transport for DNS is actually over UDP, right? As opposed to TCP, right? Because with DNS, we're just trying to get stuff fast, right? Those of you that don't know UDP versus TCP, TCP is famous for the three-way handshake, right? So hello, hi, are you talking to me? Yes, I am, right? Now we've established that we're going to talk to one another, and now we do our transaction. Whereas UDP is fire and forget, right? I just want to fire off queries. So how that works in practice is like for the client, the client doesn't care. I just want to answer to my question. So if I don't get an answer, I'm just going to ask again. Now, this can be problematic too, right? Clients can keep asking and be overly aggressive in asking. There's even things these days called DNS zombies, where we see questions that were asked months or years ago all of a sudden being asked again. In some cases, we have theories as to why this is, but if you want something fun to look at, take a look at Jeff Houston's DNS zombies talk, right? So again, back to this, there's just so much going on. Now, some of this is what I've already talked about, right? There are multiple servers by design. That's the way it is intended to be. You want to have at minimum 2 name servers per domain. Usually, 3 or more is what you want. The other thing is that's really amazing, about the DNS is it is this loosely coherent database, right? I could make a change to some record in my domain, and if I haven't lowered the TTLs, if I haven't planned this change out, then some resolver somewhere may have cached the record that I'm changing, and based on what that TTL is, it might not change in the time that I kind of want it to change, right? So if you become a DNS admin, this is, back in the old days, this was definitely one of the things you just tried to track down all the time. I've made a change. Why hasn't it propagated? Why hasn't, in terms of authoritative servers, there is a primary server. That's where you insert the data. And then there are, usually a large number of secondary servers, right? So sometimes there's problems with that data change on the primary propagating down to the secondary. And then sometimes it's some resolver has this cached, intermittent problems are the most fun to debug. Yes, I think we can all agree on that. But, this whole thing of sometimes I query the server and I get this answer, and sometimes I query and I get that answer. Those are really hard problems to track down. Such is life in DNS world. But again, 30-plus-year-old protocol. We can't just, anytime we want to make changes to the DNS, it's an add-on, right? We can't just say on this date we're going to make, lots of changes to the DNS. It's core design, right? These are all added incrementally. Some of the big ones that have been added, I've listed here. Notify is an important one, right? In the old days, you relied on timers in the SOA, the start of authority records. So essentially on the primary, I would have, I can make a change. And as these timers tick down, secondaries would check in and see if there had been any change on the primary. And if it had, they do what's called a zone transfer, and they would get updated data. Of course, these days, you want, anytime you make a change, you want it to go out immediately, right? So this is what notify is for. So now in modern DNS, anytime I make a change in my zone or my domain, you'll hear those two words used a lot interchangeably. But anytime I make changes to my zone data for my domain, usually I want those to go out immediately. And notify is a mechanism by which those existing timers are automatically tripped to 0. And the primary sends out a notification that, hey, you should check in with me. You secondary, please check in with me because probably I have newer data than you. The other one is DNSSEC. Now this is a long one to talk about, right? I could spend another hour just talking about DNSSEC. I won't, but again, DNS security was not, in the original design, right? So again, you start thinking about, if you go back to those other slides, you start thinking about things like, I'm the client. How do I know I'm asking the right resolver, right? How do I know I'm talking to the right resolver? I don't know. That part is actually a little trickier than what we've done with DNSSEC, but if you go back up the chain here, how does the resolver know that I'm actually talking to a real root server? How do I know that I'm talking to a COM server? How do I know that I'm talking to the authority, for example.com? The way this was done is, the way this was fixed was DNSSEC, right? So there's been several cases of cache poisoning in the history of the internet. That's another fun thing for you to research, after this at your leisure. The Kaminsky attack is a big one. That was a scary moment in DNS history. We solved that. Really, it's, in all intents and purposes, we solved it, right? That's an attack that can still happen, but it's like lab-based, right? We added some randomness, query source port randomization. We added, anyway, as a fix to that. The real fix is DNSSEC, right? So for DNSSEC, you can think of, just like if we looked at these node trees and in the earlier part of the talk, and we talked about the chain of authority. For DNSSEC, we established what's called a chain of trust, right? So it's a really clever way of establishing cryptographically provable mechanisms by which we know that the response came from the entity that it was supposed to come from, and that the data has not changed in transit. Okay. So DNSSEC is the solution to cache poisoning. Again, we did query source port randomization for the Kaminsky attack. What I'm trying to get at here is DNSSEC is not fully deployed. It's been around for, my goodness, 20 years now, but it's not fully deployed. The reason being is, operationally, it's pretty complex, right? Authoritative servers have to do additional work to implement DNSSEC, right? And then operationally, on the left-hand side of the screen, over on the resolver side, if someone on the authoritative side breaks their DNSSEC, it only gets reported usually to the folks that are operating the resolvers, right? So there's operational burden placed on the ISPs, et cetera, that run resolvers. And so some have decided it's not worth the risk. Okay. I'm not going to get into the layer 9 issues on that one, but DNSSEC, has been around a very long time. It's very solid. It's gotten much easier to deploy, particularly on the authoritative side. And this is one of the questions that you want to look at, right? Is your provider providing you with DNSSEC, right? I happen to live in a neighborhood that has Google Fiber, so my connections or my queries go out to Google, and guess what? They do DNSSEC. So, but depending on who your ISP is, maybe DNSSEC is not being provided for you. So again, this is stuff that I encourage you to think about. All right. A couple of other ones that are kind of big that you need to know about. So eDNS is extension mechanisms for DNS. So again, we're still running on a lot of those core designs of the DNS. One of those was that a DNS message max over UDP was 512 bytes. Now, as the internet progressed and we had things like DNSSEC and IPv6, these DNS messages got larger, right? Particularly with DNSSEC. So eDNS is a way to extend that to up to 4096 bytes, right? Again, back to this thing, eDNS is a hop by hop protocol, right? So every name server along the path that you're talking to is establishing what size DNS messages we can send, right, over UDP, right? So there's a lot going on. ECS is eDNS client subnet. This is a mechanism by which, these days, if you think back like in the history of the internet, in the old days, obviously almost always we were giving the same answer in the DNS to whoever was asking. But these days, there are a lot of reasons that you want responses localized, right? Ads is another big one, right? If I'm, if I'm searching for something or whatnot. Anyway, there are reasons that you would want to give a differing answer for the same query. So if I'm running a grocery store, for example, domain, and folks are visiting my site, I might have different items, right, in one area than others. So one of the ways we can do that is providing different answers based on the location that you're coming from. Now, the DNS, right, I've just scratched the surface on the complexity involved, right? Because when you start doing things like ECS, then suddenly there's more privacy concerns, right? If I'm not doing ECS and it doesn't matter where my query is coming from, then the authoritative server doesn't need to know where I am on the network. They're just going to get query and answer, right? They'll know where my resolver is, but they won't really know anything about my network. ECS changes that, right? So there's more privacy concerns there. So as with everything, right? There's pros and cons, right? There's push and pull. You're getting something that maybe some users want, right? Because they want to be fed more specific data. And then you're getting some stuff that some users very definitely don't want. They don't want any information about their location, their networks being provided to authoritative servers. And then these others I've mostly talked about. Anycast DNS. Again, Anycast is very simply routing magic. Right, it's a way that I can set up multiple servers that answer to the same IP address, and based on where you're coming from, whichever one is closest to you network-wise, not necessarily geographically, but network-wise, that is where your packet will be delivered, and that server will then be responding to you. Again, all these crazy lines going everywhere. Load balancers we talked about. I think They certainly are involved in the DNS. DNS firewalls is interesting, right? So this is a mechanism by which, and I'll just put this term out there for you, RPZ, so response policy zones. This is a way that you can do things like typically for like the benefit of your client, right? If a client, if you think about like the enterprise situation, you know, prior to COVID, when we all went to an office, you know, sometimes just bringing in and out of devices, you know, someone may have gone to a Wi-Fi, you know, coffee shop or whatnot, and they clicked on the wrong thing, and guess what? Now they got some malware or whatever. They bring that device back into the corporate environment, and you don't want that device really doing anything on your network. And one of the things you can do is with a DNS firewall, right? Malware has very specific things that it tends to ask for in the DNS. So you can kind of tell pretty, you know, quickly that if this question is being asked by a client, something is amiss with that client, right? So you can do things like either not answer that question, or, you know, send folks to, you know, sort of a captive portal thing that says, hey, call IT, right? And then some people use DNS firewalls to filter out, you know, content, right? So someone mentioned in the chat earlier about, you know, dangers for those that are under 18, right? So they're you know, age-related things that you might want to filter out content. So typically these DNS firewalls exist on the caching resolver, and there are feeds that that parties maintain, and so you can enter in a relationship with a party to, some of these feeds are free of charge, some of them you pay for, but it's a service that then, for example, ISPs can offer to their customers, where certain kinds of traffic based on DNS name are not served to the client. So in closing, first, thanks everyone for joining. Thanks NANOG for having me. I really encourage you to, like I said, start thinking about where your DNS traffic goes. You know, if you really want to get into the DNS, install a name server on your laptop and use it as your resolver. You can do your own resolution on your own laptop, right? You don't have to rely on the ISP or any of the free services to do that. You can do it yourself. That's a great way to start learning, because guess what? It's going to break, and then you're the one that has to fix it, right? So if you are really in a pinch, you can go back to using your ISP's DNS, or you can sit there and try to figure out, you know, what's going wrong. So question is 9.9.9.9 quad 9 essentially acting as a DNS firewall? In its purest form, quad 9 is providing you with just a place of resolution, right? The idea behind quad 9, some of it is, you know, it goes back to, and I don't want to get too heavily into it, but it goes back to what parties you trust and what parties you trust with your data. So I can learn a lot about you by knowing what you're asking for, right? If you're, whatever you're looking up, you know, tells me a lot about what you're interested in. You know, in the sense of how the internet is monetized, right? This usually is ads, right? But there's other concerns, right? If I'm in a country where I don't agree with the government, blah blah blah, you know, and you know, some folks learn things, you know, or look up things to their potential detriment, right? So they don't want to use, you know, their ISPs name servers in that case, right? So anyway, this is a long answer of saying I'm not sure. I'd have to look and see if Quad9 app actually offers DNS, what's traditionally called DNS firewalling, as in not serving certain types of content to you. But usually when we talk about DNS firewalls, we're talking about feeds that are given to you, right, or sold to you or provided to you. There's lots of companies out there, like Spamhaus, Detect. There's Farsight. There's lots of folks that their entire effort is finding what are malicious domains and then providing those as feeds to people that take them in, and then that protects their customers, right? Not sure if Quad9 offers that kind of service, but potentially. All right, that was a good one. Any other questions? While you're typing them in, again, think, I've said this a lot, but think about where your queries are going, right? Do you trust the party enough that you're sending your DNS queries to, right? Let me see. Okay. Okay. We've not gotten any more questions. So again, I want to thank everyone for joining, and thanks to Edward and Lee at NANOG for having me. And I look forward to seeing you all in person at NANOGs once we are able to meet again. I really do look forward to it. Be on the lookout, I will say, for like NANOG outreach. So it's not just the NANOG meetings. There are often more local NANOG events. So just be on the lookout for those. And again, look forward to meeting you all in person. Okay. All right. Thanks a lot. Take care.